Hi guys, I'm Lázaro Padilla. I'm a professor of physics at the Universidade Estadual de Campinas in Brazil. And in this talk today, I'm going to discuss with you two-photon absorption in nanomaterials. I'll make indeed a brief introduction, of the process, and describe and discuss with you also what's the state of the art of these processes in nanomaterials. So thank you for watching this talk today, and I hope you enjoy it. So, before talking about the process itself, let me just introduce a little bit about our lab. I'm the head of the ultrafast spectroscopy lab at Unicamp in Brazil. We are located just outside of São Paulo City in one of the most prestigious universities in Latin America. Our university has just founded the first photonics research center uh, in Brazil. We're located in at the Physics Institute, and it's called Photonicamp. It's Photonics Center at Unicamp, and in this nice white building here, what we do is a lot of research in optics and photonics, including integrated photonics, silicon photonics, advanced spectroscopy, quantum optics, and all sort of interesting stuff. My lab, the lab I lead, uh, is focused on ultrafast spectroscopy, which is basically we study optical materials and use advanced spectroscopy techniques to do so. Uh, and here is just to show a little bit of what's our group. A very recent picture of our group. These are the guys who has done the work I'm going to show to you here today. So before going on, let me just make a very short introduction of what nanocrystals or quantum dots are. These interesting guys here that are responsible for the Nobel Prize in Chemistry this year, given to Munjibo Wendy from MIT, given to Lubrus and to Ekimov for the synthesis and of these guys here more than 30 years ago, and that revolutionized all the nanoscience. I could say like this. And these guys, they are very tiny pieces of semiconductors uh, in which the exciton generated, they are confined in 3 dimensions in a way that you can, if you just do some very quick quantum mechanics calculation, you realize that the band gap for this material scales with 1 over r squared, where r is the radius of this nice little guy here. And because of that, so by just changing the size, you can tune the absorption and emission of these materials. And with that, you can gain a lot of flexibility to produce materials that can be used as light emitters and light detectors. So the tunable band gap is one of the key features of these materials. Others are basically the high PL quantum yield, because you can actually play with the surface in a way that you can eliminate defects and make these guys having quantum yields near unity. And furthermore, you can do surface and shape engineering in the way that you can basically manipulate how excitons behave inside of these guys, and you can control then multi-exciton interaction, light matter interaction. You can basically uh, gain a very important set of degrees of freedom to improve the way this material behaves in terms of light absorber or light emitter. So they become very interesting materials for applications. Uh, and when I say interesting for applications, before I go to specific types of applications, I want to actually mention to you the work from this lady, Maria Goppermeyer, who in about almost 100 years ago, proposed on her very remarkable PhD thesis that it would be possible for an atomic system go from a state M to a state N, or from a state N to a state M, by the interaction with two photons. We are very used to the idea of you being excited to from a fundamental level to an excited state by absorbing one photon, and then by going back from the excited state to the fundamental level by emitting a single photon. Maria Koppermeier proposed that it would be possible to do the same process going from a state M to a state N by indeed emitting two, three, four photons. Or on the other hand, you could also go from a state N to a state M by absorbing multiple photons at the same time. And this was predicted by her in 1931, and she won a Nobel Prize for that. And in fact, more than 30 years later, with the advent of lasers, it has shown that her predictions were correct. And why a material can absorb two photons at the same time? Basically, that's because no physical system sits on a parabolic potential. And we can say that the linear absorption or the linear optics that we are used to is an approximation for weak fields, which is basically the same as we think about the Hooke force Hooke model for the mass string system, which the force is proportional to displacement r. So when you are in the weak regime, your potential faces a parabolic shape. However, when you have a strong enough field or strong enough displacement here, you can find non-parabolic potential. Same way in optics, when you drive the field, or you drive the electrons with an electric field high enough, you can in fact write the polarization you're going to create in the system as epsilon naught times chi1 times E, where this is the approximation for the linear part, plus nonlinear terms, where, for example, chi2 times E squared is the first order of the nonlinear process, which is the second order response. The third order response is chi3 E to the cubic, and so on and so forth. And if you have a system that it's symmetric, it means that the potential is the same this way and that way, the first non-zero term would be the first non-zero nonlinear term. Okay, of course, the chi1 is non-zero, but chi2 will be zero, and the first non-zero is chi3. Okay, and chi3 is very interesting also because you can think of this guy and write it specifically in terms of electric field, which is E naught cosine omega t, right? If you propose electric field like this, very simple way, what we're going to learn is that E cubic can be 1/4 E naught to the cube cosine of 3 omega t plus 3 cosine omega t. In other words, the polarization that you create will have a term that oscillates with 3 omega and a term that oscillates with omega. The term that oscillates with 3 omega is called third harmonic generation. So you're going to create a polarization that will oscillate with 3 times the energy of the driving field, which means that you're going to have a generation of what we call third harmonic. So the polarization will be written like this. Now the question is, what is this? What oscillates with the same frequency of the driving field? That's this term, which can be written as epsilon naught chi3 omega 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 minus omega modulus squared of the electric field times the electric field. In other words, if you rewrite the total polarization, which oscillates at omega, we are going to have P1 omega plus P3 omega, which is going to be written as epsilon naught chi1 omega, E omega plus epsilon naught chi3 of omega, omega, omega minus omega, modulus square of E times E. Note that this is proportional. This has this factor times E, and this has this factor times E. And we can rearrange this and call this chi1 and call all this a delta chi. So this is a perturbation to chi. And this guy refers to the linear absorption in refraction. Meanwhile, this guy corresponds to what I call nonlinear refraction and nonlinear absorption. In fact, if you write down the math, you're going to realize that the real part of chi1 is proportional to the refractive index, and the imaginary part of chi1 is proportional to the absorption coefficient. Now, the variation here, this perturbation to chi, is responsible for a term that is proportional to the irradiance coming to the sample. And we call this N2, which is the nonlinear refractive index, and alpha 2, which is the nonlinear absorption. And it's called alpha 2 simply because you require 2 photons to do this process. And this process, basically, alpha naught is when your energy is above the band gap and you go with 1 photon from the valence band to the conduction band. Alpha 2 is when you take 2 photons put together instantaneously and go from the conduction band from the valence band to the conduction band. So one thing that's interesting is that if you have a focused laser beam, the irradiance is proportional to z to the minus 2, or z here is the beam waste, right? On the other hand, if you think about fluorescence or emission, right, you're going to think that this is proportional to the irradiance for linear absorption times the how much the material absorbed, which is proportional to alpha. So if you think about the emission caused by two-photon absorption, you're going to realize that's proportional to I squared. So the emission due to two-photon absorption is proportional to the z to the minus 4, which means that you can get very good resolution on two-photon with emission excited by two-photon if you have a focused laser beam. So, and people have explored this in the past for like 20 years to use two-photon absorption or two-photon excited photoluminescence to look into materials for imaging with 3D resolution. For example, in this very interesting paper by the group of Webb in 2003, they actually shown that it's possible that they actually used cadmium selenide quantum dots to actually image in vivo some mouse cells and show like very good resolution for that using these bright nanomaterials. Also, you could explore two-photon absorption and emission to use, for example, these nanomaterials, those quantum dots, to do two-photon pumped lasers, for example. And these are like the very first work, for example, in two-photon pumped lasers, the work in 2008, the in vivo bioimaging using quantum dots by two-photon excitation. But after that, a lot of research has been done in this field, and there are many, many advances, and people are reaching very low thresholds. You can reach thresholds below 1 millijoule per centimeter square for two-photon pumped lasers in systems like in microspheres using for as a resonator or a VCSEL or things like this. Also, people have been doing a fair amount of work to look at two-photon absorption uh, for enable 3D bioimaging. For example, this work uh, people have been looking, for example, in perovskite quantum dots covered by silica to to mark cells. Also, other materials that are very interesting on this end are, for example, copper indium disulfide, because they're free of heavy metal and they have a much better cell viability. For example, if you compare copper indium disulfide with, for example, perovskite quantum dots, you can compare here that CIS can reach basically 100% viability, while for even when you cover then the the perovskite quantum dots with a silica layer, the cell viability drops as you have high concentration. So these last two slides were just to show you that there are interesting research done in quantum dots and two-photon absorption. Uh, and the advances on this is not just because you can use this in applications. It's not just you can just go ahead and build some device out of it. In the lab itself, it has proven to be a very interesting tool, because when you think about two-photon absorption, if you think about perturbation theory, if you have done a quantum mechanics course, you're going to realize that the transitions for two-photon absorption obey different selection rules than transitions by one-photon absorption. This way, if you have material with very well-established symmetry or paired symmetry for their wave functions, you can have uh, transitions, different transitions for two-photon and one-photon absorption. And people have explored this, for example, to understand what's the band structure of nanomaterials. Here, I just showed to you a brief example for when you compare perovskite nanomaterials, where you have the first one-photon absorption here, the first two-photon absorption right there. For cadmium selenide, this is even more clear that you have the one-photon absorption here, the first two-photon absorption peak right there. And this occurs because of this difference in parity of symmetry for the one and two-photon absorption, the way that the two-photon absorption mostly occurs at higher energy than one-photon absorption. For CIS, for example, this is inverted. You have a first weak two-photon absorption peak here below the one-photon absorption peak. And note that here I'm talking about transition energy, okay? So if you want to talk about the photon energy, of course, the energy of the photon for the two-photon absorption is half of the energy shown here. For example, for this guy here, where it's 2.5 eV, each photon has 1.25 eV. So for lead sulfide and lead selenide, for example, the first one photon and two photon absorption are coincidental because of symmetry breaking, or it means that they actually have transitions for one and two photon occurring basically at the same position. So this is a tool that helps us to understand, for example, how these symmetries are held or not in these nanomaterials. Also, one interesting thing about two-photon absorption is that, virtually speaking, the optical density of a material for two-photon absorption is nearly zero because the process is very, very weak. So when you study, for example, in a ultrafast spectroscopy lab, two-photon absorption, or I'm sorry, transient absorption in nanomaterials, for example, you run into a problem that the number of excitons per dot average as you go through the sample decreases simply because you have optical density. It means that if your pump experiences an optical density of 0.6 to your sample, what you're going to see, or I'm sorry, 0.5, you're going to see that your initial excitation was 1 exton per dot. On the back surface is going to be nearly 0.3 exton per dot. So you have a beam depletion through the sample that makes pretty hard your data interpretation. Let me just give you an example. If you're studying optical gain in nanomaterials by exciting by 1-photon absorption, this is a sample with optical density at the pump of nearly 1. And you see that you're hitting 7 exton per dot on the front surface, and you barely see gain here, okay? And that's because for your high optical density, you basically depleting through all your sample path, and you're not seeing gain. Conversely, oh, by the way, here is an example. When you change the optical density from 0.2 to nearly 5, you see that you get optical gain for the small optical density, because for small optical density, your excitation through the sample is nearly constant. On the other hand, when you go to high optical density, you will never have optical gain, because you're always going to deplete more your beam than you should. So two-photon absorption comes as a tool to solve this problem, especially if you're looking into like these very interesting nanomaterials with thick shells, which the pump excitation, the wavelength for the pump has much larger optical density or much larger absorption cross-section than the probe region. That would make it nearly impossible, because see, this is the optical density for the pump. So if I have an optical density here of let's say 0.6, which would make your data already kind of problematic. But if I make it here 0.6, means that the optical density at the probe would be like 0.01, which is nearly impossible for us to actually have nice signal to noise to be able to interpret the data. So one way to do this is, if you take two-photon absorption as the optical density for this is virtually 0, you see the beam is not depleted at all through the sample. So what happened here is that if you try to measure gain, see, you get very nice gain curves here, because even for very high concentration sample, because the optical density for this is 0. And just to compare here, the same curves done by 1-photon and by 2-photon, you see the 2-photon pump, the curves fall all in the same trend, because basically the sample doesn't care about the concentration when you're exciting by 2-photon absorption. So, but the question is, how strong is 2-photon absorption in nanomaterials? Is it worth making nanomaterials to improve 2-photon absorption, to make it stronger, make it more drastic effect? In fact, if you go back when quantum dots were just starting, people were saying yes. And the answer was yes, basically because one thing that people were predicting is that the oscillator strength for a single transition would increase as you make the size smaller. And however, in our first work in 2007, when I was still in grad school, we realized that that was not actually too much true. The two-photon absorption cross-section would decrease as the quantum dot would become smaller. And the argument there was just because that's a matter of size. It's much easier for you to interact with a basketball rather than with baseball, just because the basketball is bigger. So it's much easier for 2 photons to find a basketball than to find a baseball. So the cross section for a bigger ball is higher than the small ball, and that should scales with the volume because the interaction doesn't need to have to be on the surface. It goes through the sample, through the whole volume of the quantum dot. And in fact, when we are able to take data for cadmium selenide, for example, from several papers out there and put all as a function of the volume, what we see is this very nice volume dependence. We gotta like put everything in a line here, which indicates that two-photon absorption in fact increases with the volume, and that's a linear dependence, which means that apparently it doesn't depend on the size if you think in terms of volume normalized two-photon absorption coefficient. And the reason for that is that even though every single transition increases, so you see the magnitude of a single transition, it decreases when the size gets bigger. In other words, it increases as the size gets smaller. If you take and integrate over the transitions, when you go like to the continuous or quasi-continuous spectral range, we see the other way around because you have a drastic reduction on the density of states when you make the quantum dots smaller. So there's a trade-off between increasing a single transition and reducing the density of states, which makes at the end of the day, two-photon absorption in principle is not necessarily enhanced in nanomaterials. So what is very surprising is that if you take this, we took like a collection of data, every data that we found in the literature that we find, it was data that we could understand how the authors have taken the data or what's the concentration for the samples. So the data that we could really track. And if we take all that data and put together, we get this. And this is all this data as a function of the quantum dot volume. And that's for cadmium selenide, cadmium sulfide, cadmium telluride, CIS, zinc sulfide, zinc selenide, lead sulfide, lead selenide, and a bunch of perovskites. And we see that they are all spread around here. And one thing that's important to take into account is that when you talk about two-photon absorption, I just mentioned to you a few minutes ago that actually the process involves a transition that goes by two photons that interact instantaneously with the material. But if you think about perturbation theory, what's going on is that the first photon comes and puts your electron here on a virtual level, and then the second photon comes and excites this. But what's a virtual level? Virtual level is nothing more than simply a real state level here, detuned by an energy delta 1. So if you have a material that has a smaller band gap, what happens is that even though the tuning is appearing here, this delta 2 will obviously be smaller than this delta 1. And if you run the calculation, you're going to see that this influences the two-photon absorption. Because if you remember the equation, on the denominator, it appears here, this term. So if you run the calculations, you realize that the two-photon absorption cross-section, or if you think about the two-photon absorption coefficient for bulk semiconductors, you see that should go with 1 over the band gap to the cubic. And if you do the same for quantum dots, you basically see the same dependence with the material band gap. And the reason is that basically this intermediate state resonance down here. So to make a fair comparison for this data, we take this and correct by the band gap cubic, and this becomes a much more narrow distribution, which surprises us because it actually kind of indicates that it's what really important is the size, not really the material that's made of. And they nearly fall all within like an order of magnitude within all this dependence here. And one thing that's even more interesting is that if you just think about this and divide by the volume to look at the volume normalized two-photon absorption, it's basically flat with the volume. If you want, there is a little bit of a slope here that indicates that making it smaller makes it a bit better, but honestly, this slope is pretty tiny. When you go by about 4 orders of magnitude in volume, your two-photon absorption changes by a factor. Your normal volume normalized two-photon absorption cross section changes by a factor of 2, roughly. So I could tell you that's nearly constant. And another thing that's quite interesting is that if you just look at these reddish points here, corresponding to the cad selenide, all this dispersion actually becomes much narrower. It goes in this distribution here. On the other hand, if you look at perovskites, even though they are basically the same material and basically the same size, you get like more than 2 orders of magnitude spread. Look at this, for example. And honestly, my guess here is that the dispersion for cad selenide is just much narrower than for perovskites. It's just because cad selenide has been studied for much longer time. So the mistakes people have to do, people would need to do to learn the right way to study this in cad selenide has been done in the past. And now people know what to do, what not to do. And the same is not true for perovskites quantum dots, which were created just a few years ago. And so most of these results probably will eventually, I expect that in the next few years, this will be exactly come down to some much narrower distribution than 2 orders of magnitude as it's shown here. So this is somehow frustrating because it shows that it doesn't really matter what you do with a quantum dot. The two-photon absorption cross-section is going to actually follow just a volume scaling and not much you can do about it. However, if you really pay attention here, there are these blue diamonds and these blue dots here. These blue diamonds here, that they follow something different. These blue diamonds here, dark blue and the light blue diamonds, they are for lead sulfide quantum dots. And if you look, the trend here for these guys is slightly different. Or it means that apparently it becomes smaller as the quantum dot becomes bigger. And in fact, if you look at this, for cad selenide, for example, when you reduce the size from 2.6 to 1.8 nanometer, your two-photon allowed transitions spread around the energies, making a very drastic reduction on the density of states. What's not so true for lead sulfide? And that comes from the fact that lead sulfide has a very unique type of band structure where the electron and hole effective masses are very similar, which doesn't happen for cad selenide. And furthermore, the bulk band gap is pretty tiny compared to the confinement energy, which is the opposite what you see for cad selenide. And this unique structure makes all the transition kind of move together when you make it smaller, in the way that it's not spread as it is here. They actually kind of group together. And what we see when you study lead sulfide is that, in fact, as you make it smaller, the normal volume normalized two-photon absorption kind of increase. But going back to cad selenide or perovskite quantum dots, things that are interesting to point is that this nice work from Makarov et al. And colleagues back from 2014, if I'm not mistaken, where they studied a series of different types of different size of cat selenide quantum dots. What they see is that if they normalize the two-photon absorption cross-section by the number of atom or number of molecules of cat selenide, what they realize is that especially when you go like to the quasi-continuum region here, they're not different from the bulk. One may argue that there is a factor of 2 here, but if you cut off the experimental errors, I would tell you that you are not really getting any big difference here if you compare to the bulk. They are really close. In these quantum dots, they are on the weak to intermediate quantum confinement regime, when the quantum dot size is nearly about the same as the exton Bohr radius. Conversely, if you look at the perovskite quantum dots, cesium lead bromide, on the weak confinement regime, these guys are big compared to the exton Bohr radius. You see that basically the two-photon absorption cross section here is or divided by the volume normalized cross section. Let's say it does not depend on the size, and more than that, actually the spectra is pretty similar. This data we're taking exactly at the same time using the same equipment, just replacing samples, so they are pretty similar. And more than that is, if you plot the curve expected for the bulk, you see that the data for the quantum dot and the data for the bulk are the same. Or not the data for the bulk, I'm sorry, what you expect for the bulk. They follow the same trend, which is quite interesting because it shows to you that if you're in the weak confinement regime, you are back to your bulk material, as one would expect. And indeed, that's what we see. So, okay. The question here is, we can increase two-photon absorption quantum dots, but the way to do that is making quantum dots bigger. But when you make quantum dots bigger, you change the band gap. The question is, how much can you change the two-photon absorption without changing the band gap, or without changing the emission spectra? Because for some applications, for example, for bioimaging, sometimes you want to keep your emission on some specific wavelength region. For example, this is the first transparency window for biotissues, and that's where you want to have your emission wavelength. So you would have deep tissue penetration, for example. But again, that's what happens when you make quantum dots bigger. Your band gap redshifts. So the question is, how can you do that? And other groups out there, they have thought about ways. And one way, for example, would play with the shape. For example, the group by Wagon in Germany, they have proposed that you can get larger volume normalized two-photon absorption cross-section by simply using, for example, nanoplatelets or nanorods. And their argument is that you change how the local field penetrates the nanomaterial, and then you get enhanced. You manage to enhance the effective response. When you have more field, you're going to have more nonlinear optical response. And other reasons they would speculate, and this has not been proven yet, is that you would, for example, for nanoplatelets, have different selection rules, which and the breaking of the selection rules that you would have in quantum dots in this platelet type of nanomaterial would allow other transitions that were not allowed before, increasing the density of final states and finally increasing the two-photon absorption cross-section. And their argument for that is basically because this is what you would get simply by increasing the local field penetration, and that's what they get experimentally. But you can get this, and that's all fine, but there's one problem with that. When you go to nanoplatelets, for example, you get poor quantum yield on the order of like 10 to 20%. On the other hand, you get poor photo stability also. Like they're nothing is as stable as those nice little spherical nanomaterials. So one way to try to manipulate the two-photon absorption response without playing around with the emission would be explore heterostructures. So here we explored, for example, core only, cadmium based core only, and two types of core shell. Type 1, which is cadmium zinc sulfide, and type 1 here we are talking about these guys where core and the electron and holes are confined to the core, and the quasi type 2, not quite type 2. Type 2 is when electrons are on the shell and the holes are on the core, for example. But the quasi type 2 is when holes are on the core and the electrons are on the whole core and shell. So the advantages for this quasi type 2, we have shown in the past that you can increase, when you first increase the first few layers of shell, you have some shift on the absorption in the PL, but then you can increase quite a lot your shell from like 1.5 to 5.5 nanometer, and you barely change your emission wavelength. So the question is, how much changing the shell changes the two-photon absorption? Can you enhance the two-photon absorption by changing the shell? We know that changing the shell, basically, when you go to the short wavelengths where you're in the quasi-continuum spectral range, you basically increase the linear absorption linearly with the total nanomaterial volume. But how about the two-photon absorption, the nonlinear response? So to do this, we have studied a series of core-only and core-shell nanomaterials, and we wanted to actually get a very precise, very accurate volume dependence. And the most used technique, the two-photon excited photoluminescence, which is very awesome technique. However, you get to measure a lot of stuff. You have to measure the linear absorption cross section for the sample and for the reference. You have to measure concentration for the sample and for the reference. You have to measure quantum yield for the sample and for the reference. You have to account for the inner filter effect for the sample and for the reference. And all this introduces error on your experiments. And more than introducing uncertainties, the uncertainties are different for different samples. The question here is, what if we could come up with a way that the relative error, when I say relative error, I mean if I measure 10 samples at the same time, the relative error among all these 10 samples could be reduced quite a lot. So we can do like a volume comparison if we measure everybody together. So we came up with a simple model, a simple way, very effective to measure multi-photon absorption cross-section colloidal nanocrystals. And this technique is basically take into account the saturation of the emission due to the Auger recombination. What I mean by that? Basically, what I mean is that when you get into quantum confined material and you excite more than one exciton, instead of emitting two photons, the second exciton, in fact, recombines by transferring its energy to one of the carriers for the other exciton. In this process, it's called Auger recombination, and it makes two excitons, in fact, emitting a single photon. And the original recombination is typically from 10 to 100 picoseconds, while emission or PL lifetime is on the tens of nanoseconds, which makes basically multi-extons virtually non-emissive. So here you can see, for example, for on transient absorption data, when you create multi-extons, what you see is this very sharp decay here. And when you have a single exton, it kind of lasts forever here on this 500 picosecond scale. So if you're able to saturate your photoluminescence, you basically are able to decide how many excitons you have in average on your sample, and then you basically can track down what is your absorption, or means in the case you're excited by 2-photon, you can actually verify what's your 2-photon absorption cross-section. So by assuming a Poisson distribution, you can actually run a calculations and come up with this very interesting and simple saturation curve. That's so if you plot the PL magnitude as a function of the average number of exton, you get this curve here. And if you fit this, you get the average number of exton for each pump intensity, and basically you can correlate the average number of exton as a to the photon flux and pulse width of your laser and the absorption cross section. And the pulse width of your laser and the photon flux you can easily measure. So you only have basically to measure this, you measure the power of your laser and the spot size at the sample, and here the pulse width. So basically you have 3 parameters, and all 3 parameters come from your laser. So at the end of the day, you don't need any parameter from the sample itself. So your only error to determine the only relative error between 2 different samples, if they measure at the same time, comes from the fitting parameters, not from the actual measured parameters. So especially if you have, for example, materials with very weak photoluminescence for the multi-extons, this guy reduces to this. And if you take these curves, the saturation curve, and fit, that's basically what we have. So here we have done for different types of materials. So here is for core only, this is for core shell. And if you compare our data for the core only with the data on the literature, we see very good agreement, showing that this very simple technique is very powerful. So we did this for the core shell and compared the 2 different techniques. This one that we just introduced, the MEPAPs, and the 2-photon excited photoluminescence, we see pretty good agreement. Of course, no technique is perfect, right? So this technique we just proposed, the MEPAPs, it's pretty good because it reduces the experimental error. It gives you absolute numbers without needing a reference. And you don't need other samples parameter like PLQI or concentration. So it reduces your specifically reduce your relative error when you want to compare different samples. However, there are limitations, which is more time consuming. So you see, you have all this bunch of data for 2PEP. However, you have only 3 data points for MEPAPs. And that's because each data point for this takes at least 5 or 3 times longer than each one of this. You need to have good laser characterization. So for 2PEP, you basically, if you have a good reference sample, you may not know what the pulse width of your laser is, but as you're using a reference, you don't really care about the pulse width. And now for our technique, you really need to know your laser. You need to steer your sample because you have to avoid photoionization. What may happen because you're saturating, you're hitting it with too much photon flux. So those limitations, in fact, make it more difficult to go further, but for these regions, this technique is quite powerful. So we have used this technique and look at different samples. So to understand what's the effect of core shell on the two-photon absorption. And when we did that, we see, of course, for core only, this linear dependence with the volume. Exactly well how people have seen for like the last 15, almost 20 years. Conversely, for type 1 core shell, we see a sublinear volume dependence. You see, you increase the total volume, you barely change your two-photon absorption cross-section. And the way we understand that is that when you, in fact, change the size of the core only, you really change a lot your density of states. However, that's not so true for type 1 core shell. So as you just change the size of the shell, you basically change much less your density of states. So you're not favoring the increasing of your two-photon absorption cross-section. So what about the quasi-type 2? When you do for the quasi-type 2, we see very interesting result because it actually falls in between the type 1 and the type 1 and the core only. And to rationale about this, we need to think on how the electron holes they interact in these materials. But before that, the question I ask is, so what's really the influence of the shell on this whole process? So if we do the spectra, and if we take this region here, the orange region, where this is at this energy here, the absorption from the shell didn't kick in yet. And if I take this region here where the absorption for the shell kicked in and compare how it depends on the size of the total size, one would expect that this guy would not change with the size because the absorption from the shell is not here yet. And in fact, that's what we see. In this orange region, it's basically independent of the volume. Now, for the blue region, we have that volume to the 0.3. So indicating that, of course, only here the shell influences. The same is true for the quasi-type 2. If you take this green region and the orange region, we see a slightly dependence here, which is within the error basically, which could be some dependence because if you think as the electron experiences the whole structure, you do change something on the interactions. So you change something on the density of states also. So, but you see that the dependence is, of course, is much stronger above the band gap of the shell. So to rationalize what we have seen is basically what we do is if you look at the core only quantum dots, they have a change on the density of states much more pronounced than you would have for example, core shell type 1, where when you make the total volume increasing from 2 to 4 nanometer, it changes just a little bit, while this changes quite a lot, increasing drastically the density of states and making a more steep volume dependence for core only than for core shell. So, more than that, if you look here and take the different types of structures and compare the oscillator strength of one transition and the total integrated area here on the quasi-continuum region, what you're going to see is that the oscillator strength for a single transition decreases for when you go from type 1 to quasi-type 2 to core-only quantum nanostructure. However, the integrated, we see the opposite trend because of the changes in the density of states. And so here the the full dots here are the numbers that come out from this integration here under the simulation. And here the open points, open circles, comes from the experimental data. So you see very good agreement, indicating that what we're seeing is actually this comes from actually from the changes on how the density of states change in different types of binary structure. And more than that, if you look closely to this data here, we can fit the volume dependence with a regular with a single linear fit. However, if you look closer to this, and if you want to see it, you'll notice that if you fit just the first few points, you get a slightly smaller slope, and if you fit the last few points, you get a different slope. And in fact, it suggests that the bigger the shell compared to the core, the steeper is this dependence. And that, in fact, could suggest that if you would have a smaller core, you would have a higher volume dependence. To try to test that, we have studied a different set with a smaller core. And we see this interesting behavior here, which the dependence of the cross-section with the volume goes nearly to the same that we see for core-only quantum dots. And in fact, what we believe is that the core shell here is becoming, basically, if you think about this effectively, this is a core only made of cat sulfide, pure cat sulfide. In fact, here, if we compare our data for the small core heterostructure with core only cat sulfide data from the literature, we see very good agreement. So suggesting that, in fact, this is the case. So basically here, now we do have all those results where we look at the data for the core only and the core shell quantum dot, and we see how it changes with the volume. They follow basically the same volume dependency, nearly linear dependence. And meanwhile, this guy, to change the absorption cross-section by a factor of 5 nearly, you really shift quite a lot the emission in the band gap. So that's not the same for the heterostructure, because you keep basically the emission on the core, so you can actually increase your total volume by nearly nearly an order of magnitude and change very slightly the emission spectra. And in fact, if you take this sample here with 2 nanometer core, it emits at around 600 nanometer, which is about the same emission spectra for the core, the quasi-type 2 sample with a 1.5 nanometer core. And but if you compare the two-photon absorption cross-section for them two, you get over about 1 order of magnitude enhancement. So we actually learned a way to decouple two-photon absorption cross-section and emission wavelength, and we can get like an order of magnitude change in the cross-section by simply playing with the heterostructure. And we can see this in a better way if we plot the two-photon absorption cross-section as a function of the emission wavelength or emission energy here. You see for the core only, it really moves the emission energy, while for the heterostructure, that's not the case. Also, when you change the cross-section, we change the absorption cross-section by changing the volume. And this can be a high price to pay if you thinking about applications, because some applications, what you're interested is in the total two-photon absorption coefficient, which is proportional to this two-photon absorption cross-section divided by the nanocrystal volume. And of course, when you increase the cross-section here, you're paying the price of increasing the volume. But if you think, for example, in applications like two-photon bioimaging, right, for 3D bioimaging, you are interested on this ratio times the total photon flux. Sorry, not the photon flux, the PL quantum yield. And if you do this and plot this figure of merit here as a function of the emission energy, what we see here is that it's, again, better for the core shell structure than it is for the core only, simply because even though this ratio becomes slightly smaller, but the quantum yield is much larger for the heterostructure. Another step forward on this is to look into structures that are not spherical. What's the case for the dotting rod nanoparticles, in which the shell is this rod shaped. And if you remember the beginning of this talk, I mentioned that people have shown enhancement of two-photon absorption by changing the shape. And so here we want to look at how the shape and also the position of the core interferes with the two-photon absorption cross-section. We have done these studies, and we've seen that apparently they split in two different behaviors here, one volume dependence here and another one right there. And the difference between these samples here and these samples there is basically that here the quantum dots are near the center of the nanorod, and these ones are on the tip. And to rationalize this, what we believe is that basically when you're in the tip, the quantum dot actually is farther from the total volume of the nanorod, in the sense that we can define this effective length, like the two lengths squared divided by the total length. And we see that the longer the effective length, the smaller is the volume normalized two-photon absorption cross-section. And you think about this, is that if you move the core farther to the tip, what may happen is that you might have defects on the surfaces or any other types of effects that cause some electric field that might make electrons and holes to be apart in a way that the wave function overlap decreases, decreasing the chance for you to have absorption. So to look at these guys here, also we have compared the two-photon absorption as a function of the volume, and take this comparison and put together with the spherical materials. To do so, we need to actually rescale the two-photon absorption for nanorods by a factor of 5. And that comes because of the anisotropy of these guys. They are not the same in different directions. If we do so, we see that, in fact, the dotting rod structures, they actually have higher two-photon absorption cross-section than the spherical core shells. And that probably comes from the fact that you have higher penetration of the electric field. So we can close this by simply put together the data for the dotting rod with our chart that we have for the core shell and core only, and see that there is very good enhancement, also the volume normalized, or I'm sorry, for the two-photon absorption cross-section compared to regular quantum dot at the same wavelength. So I want to finish this talk by telling you that, yes, it's possible to change the two-photon absorption cross-section in nanomaterials without changing the emission energy. And there's a lot of interesting physics still to study in this field. For example, we still have to learn if it's possible, for example, to really enhance the oscillator strengths for these guys in order to have pretty high two-photon absorption cross sections. And in this route, it's probably important to understand what causes the enhancement in nanoplatelet type of structures. So for the core shell structures, the best strategy you have learned is that making a core much smaller than the shell, and you can have pretty good volume dependence. So I just want to close this talk by thanking the people who pays for this research. Leave you with a nice picture from my group again. and thank my colleagues, Joseph Planelis and Juan Clement from the Universidad Jaume I from Spain, who did most of these calculations for these works, and my friends Wang Kibe and Do-Si Lee from Korea, who are our collaborators and friends who makes all these very nice and interesting samples. Thank you for watching, and see you in the next time.